Okay, so there were a couple of things we had already derived. We had seen that the current was proportional to the moving charge density, the drift velocity, and the area. And then we said that the drift velocity was actually proportional to the electric field. Well, this is, in a sense, another expression of the Ohm's law. And then we said that the conductivity that we had defined before is actually in terms of these parameters E, N, and alpha, just multiplied. So it gives us that the current is actually given by sigma times E times A. Or if you divide by A everywhere, you get the current density is just sigma times E. In fact, since the current density will be in the same direction as the electric field, this is a vector equality. Both the magnitudes of the current and sigma times E, they are equal, and the directions are equal. This is still another expression of Ohm's law. Now let's do some examples. This is question 25, chapter 25, problem 30. Now, we had discussed the resistors, which are just long, thin cylinders. Now, what if their shape is different? Suppose we have a hollow cylinder made with some material. Now, if they have such shapes, the resistance will be different if you are sending the currents in this direction or if you are sending it from the inside out. So first, let's look at what will be the resistance of this system. So let's say this is our cylinder, and we send current radially outward. So J, the current density, is radially out. What will be the resistance of the material? Now, what we know is the resistance of objects that have a fixed cross-section, A, and a given length, L. In this case, we know that the resistance is resistivity times L over A. But you see here in this cylinder problem, as the current is running away or running radially outward, the area is actually changing. So you see, if your charges are over here, you can imagine that this is the area. If they are over here, this is the area, perpendicular area in a sense. So the area is not a constant. The length, well, it will be probably this one, but it won't be linear. But we can still convert this problem into one that looks more or less like this. So let's see, the area as you are going radially away from the center will be changing, so we cannot really identify a single area. What we can do is, if we divide this cylinder into very thin shells, each one of those shells have a definite area that the current crosses. So if this is my cylinder, empty cylinder, I just divide this empty cylinder into many cylindrical shells. Just pick one of them that has a, let's say, radius r. So that cylinder, let's say that is this one, that cylindrical shell. very thin. It has almost no thickness whatsoever. It's just this shell. And the current is running, crossing this area perpendicularly. Well, if I open it up, the current is running through this area. But this is nothing but a resistor which has a fixed cross-sectional area and a given length. I can just use this expression for this opened up cylindrical shell. Okay, so let's see. What is the area of this? What is the cross-sectional area? I don't know, if I cut it like this, it won't be rectangular, for example. So the area, just asking you what is the area of this doesn't really have any meaning. If you just look at this material, what is the area? Doesn't really have any meaning. We have to be a bit more careful in defining those concepts. So here, the area is actually the area through which the current is running. So you see here, I'm sending the current in this direction. So that is the current is crossing this area. That is that area. And for how long does the current travel? The current density. Well, the current density travels a distance L. That is this number over here. So in a sense, the resistance of a given material is proportional to the length through which the current has to travel divided by the area that the current is crossing perpendicularly. No? Okay, let's go back even more. We define this concept of the current density. So does then the concept of the current density make sense? So essentially we define the current density as the current divided by area. The current is cross-passing an area. So it's just you just divide the total current by the area, you get the current density. But just like when we were discussing the Gauss law, we had defined the electric flux, and we said that, okay, we have to multiply the electric field by the area to obtain the flux. Similarly here, to obtain the current, we multiply the current density by the area, but the area has to be the perpendicular area. Do you agree?
Perpendicular to the current?
Perpendicular to the current. So actually this relationship is this one. So it's just a scalar product of the vector current times the area vector. This is the same area vector that we also define in Gauss law. Now let's look at this problem. How did we solve this problem? Well, we said, okay, let's say there is a J running through my circuit. Let's also make one more assumption. The J is uniform through the area. So the total current is just J times A. That is the total current. Now, how do we define the resistance? Well, the resistance is defined as the potential difference divided by the current. So you just send the current and then ask the question, what is the potential difference that created that current? Well, what is the potential difference? Well, it's the electric field multiplied by distance. Well, in that example, we want to find the potential difference between those 2 points. So the distance is actually L. That is the potential difference. So now we can write down the resistance of the system. Well, the resistance is, the potential difference is E times L, and J, the current is the current density times A. But the Ohm's law states that J is sigma times E. The electric field times the length is equal to sigma times the electric field times the area. These cancel, so the resistance is 1 over sigma L over A. This is another way of deriving the resistance of the material. From this Ohm's law, we stated that this is the Ohm's law. Well, this leads to this definition of the resistance. Now, if you go back to this example, to the example of the cylinder, some of the steps we did there will not hold anymore. Well, let's go back. Which step will not hold? I is equal to J times A. Will it be valid in my system? Why not? You see, A will be changed, as your friend, you see, in the case of the cylinder, I'm sending a number of electrons. That number of electrons is the same. They will lose energy, but their number will still be the same. So I'm sending a number of electrons. And the density, the current density is essentially the number of electrons per area. That's how we define it. The current is fixed. Here I have some area, and a current I is passing through that area. Well, if I look at a larger area, still the same current will be passing, because the current will be determined by the number of electrons that are moving. And that number is fixed. So the current will not be the same, will be the same everywhere. But if current is the same everywhere, A is changing, the area that the current is passing is constantly changing. J will also be changing. Well, in a sense, this will still hold, but J will be the current density at a given distance. Area will be the area at a given distance. Only without that assumption, the first relation will still hold. This is the general definition. Essentially, it just defines it says that the resistance is defined as you create a potential difference, V, and measure how much current it creates, I. The ratio is the resistance. That is the definition of resistance. So it will still hold. But you see, J will be changing as a function of the distance. J will be changing as a function of the distance. Conductivity is a property of the material itself. So this is a constant. But this tells me that the electric field should be changing as a function of the distance from the center. So if the electric field is changing as a function of the distance from the center, the potential difference is not just electric field times the distance. Because this is true only if the electric field is a constant. So this will no longer hold. So that's the problem. Now let's first try to solve this problem using what we had done over here. Just try to modify these to the problem we have. Well, let's see. This is my cylinder. I will be this much. I is a constant. So at a given distance r from the center, there is this area A through which all of the current passes, so the current density is smaller. Now, what is A of R? The surface area at a distance r from the center that the current is passing through. It's just the area of the cylinder. 2 pi r times L, whatever the height of the cylinder is. So now I can determine what J of R is. It's just I over A of R, which is I over 2 pi r times L. This is the current density at a distance r. Now, I know the current, but what I need to find is the electric field and hence the potential. Well, once I know the current density, I know the electric field. It's just J of R over sigma, or rho times J of R. This is the electric field at a distance r. Now I can calculate the potential difference. This is E dl from a distance r1 to a distance r2. This is the potential difference corresponding to that current. Well, let's put everything in. It's rho times I times 2 pi L. These are constants. I have dr over r from r1 to r2, which is rho I divided by 2 pi L logarithm of r2 over r1. This is the potential difference. Well, you see, when we are defining the resistance, we don't really care about the signs. The resistance is defined as positive. So that's why I just ignored all. From the definition, there is a minus sign over here. You see, the definition of a potential difference was minus E dot dl. But since we are only interested in the difference here, not the sign, I just ignored the signs. Well, V, by definition, is I times R. So this tells me that the resistance is rho over 2 pi L times logarithm of R2 over R1. Well, you see, this is the area, the side, you see. Let's look at this, what this area is. It's not the area of this disk. Here we have a cylinder. And the current is running through the side area of that cylinder. So that is why I have the area is 2 pi r, this is the circumference of the cylinder, multiplied by L, the height of the cylinder. This is the side area of the cylinder. You see there, this dashed line is actually this area. The current is running through that area. So this length is 2 pi r. This length is L. Which thickness? A. Well, you see, that is an area. Area doesn't have a thickness. No, I mean, this is an alternative derivation. Now I will go back to that thickness. This is one way of deriving it. So you see, the steps over here is, first, from the given information, you identify the current density at every point. But once you know the current density at every point, Ohm's law tells you what the electric field should be at every point. In this case, it will be radially outward and depends only on the radial distance from the center. Once you identify the electric field, you find the potential difference. It's just the integral of the electric field. But the potential difference has to turn out to be proportional to the current, and that proportionality constant is what we call the resistance. So this is one strategy to calculate the resistance of materials with arbitrary shape. Whatever the shape is, if you can determine the current density at everywhere, in the question it should be a given somehow, then you can determine the electric field and calculate the potential difference. The potential difference divided by the current will give you the resistance. Now in this problem, an alternative derivation would be this one. You see, we have this cylinder, a thick cylindrical shell. And, well, it is filled here. Now, I just imagine it as a collection of much thinner concentric cylindrical shells. I just divide it into smaller shells. Or from the side view, all of the shell is just the sum of much thinner shells. Now, the definition of R doesn't change. It's V over I. V is the potential difference between the starting of the current to the end of the current. So let's say this is point A, this is point B. V is equal to VAB. Absolute value, because I don't really care about the sign. Now, of course, this VAB I can just obtain by, well, that point and this point will have, in this given problem at least, this point and this point has the same potential, so it's an equipotential surface. So the total potential difference between these 2 points will be the potential difference over here plus the potential difference over here plus the potential difference over here, etc. So the total resistance will be V1, let's say V2, V3, or I don't know how many rings you have, but the current running through each one of those very thin shells will be basically the same. The current running is I. So this will be R1 plus R2 plus Rn. The total resistance will be just the sum of, in this case, each R1 is the potential difference in a given shell. This is V1, this is V2, this is V3, this is Vn. So the total potential difference is just the sum of all of them. R1 is just V1 over I. Well, V1 is this potential difference. I divide by the current, so that gives me the resistance of this inner shell only. Then I add the resistance of this second shell, the third shell, and I just add up all the shells. Now, each one of them this time I take a very thin shell The radius is r, thickness is dr. Now, within this thickness dr, electric field is constant. It's so small that electric field doesn't change at such a small distance. But if the electric field doesn't change in a very small, within my conductor, let's say, then the resistance is given by rho times L over A. If the electric field doesn't change within my conductor. This is the resistance. Here, L is the length that the current runs through. Well, in this case, it's just dr. Well, the area, again, area is the area through which the current runs. It's the side area of this cylinder, which is 2 pi r times L. So this is the resistance of this very thin shell. The total resistance is just the sum of all these, which is rho times rho over 2 pi r L dr from R1 to R2. Well, essentially, I'm doing the same thing in both of the derivations, but in this derivation, I'm not even mentioning the current density. Yes?
Why isn't electric field changing?
Sorry?
Why isn't electric field changing?
Well, the thing is, it's so thin. Even if the electric field is not uniform, within that very small range of values of R, it will basically have the same value. You see, even if, let's say, a function has, even if you have this function x squared is almost constant if x is between, let's say, 10 to the power 6 plus 10 to the power minus 10 to the power minus 6 and 10 to the power 6 plus 10 to the power minus 6. Within these values of x, that function doesn't change. That is why I'm using, you see, over here. Eventually, I will take dr to 0 when I'm converting it to integral. So compared to r, this is negligible. So the electric field doesn't change in this very thin shell. My radius doesn't change within my shell. That's why the electric field doesn't change. Again, the same system. But this time the current is running in this direction, not radially outward, but parallel. What is the resistance? Any ideas?
Is the center hollow?
Hmm?
Is the center hollow?
Well, there's a hole over there. This is a cavity. The same problem. In the previous case, the current was running radially outward from inside out. Now it's running parallel. Yes, the current is perpendicular to the area. The area doesn't change. The current density doesn't change since the area is not changing. So actually, it's just as if, having a cavity here doesn't make any difference. So the resistance is just rho times L over A. What is the area? This is the area. So it's just this filled area, that is my resistance now. Any questions? You see, if you go back to these two alternatives, let me repeat. In the first one, what we did was we first identified the current density in terms of the current. Then from the current density, we found the electric field. And from the electric field, we calculated the potential difference. And the ratio of the potential difference to the current gave us the electric field, gave us the resistance. In the second alternative, what we did was we first divided our system into smaller parts which had a constant area and constant length. That was the trick. So when I have these very thin shells, these very thin shells has a constant area through which the current runs, and the length is fixed. So I can use this expression for the resistance and then sum them up. If, for example, you have a problem where, let's say you have a cone, you have a conic shape, and you are asked to find the resistance, well, you can do whichever one you like. In this one, it will be easier to first divide this thing. Well, let me just remove this three-dimensional thing. Let's say it has such a shape. If you want to find the resistance, you can just divide it into very thin disks. Each one of these disks have the same constant area and a well-defined thickness. So for each one of these disks, you can use the R resistance is equal to rho times L over A, and then sum them up. It will give you the total resistance. Now let's look at another problem from chapter 25, problem 38. It's given that you buy a 75 watt bulb, light bulb, in Europe, which means the potential difference is 220 volts. And then you take it to the US, where the potential is 120 volts. What will be the relative brightness compared to a US bulb labeled 75 watts. So basically, you have a light bulb that is labeled 75 watts in 220 volts. But then you take it and use it for 120 volts. You don't use it with 220, but just 120 volts. So how much will its brightness be different compared to another light bulb, which is designed to work at 120 volts with a 75 watts? Now, how can you compare the brightness of two light bulbs connect to the same voltage? Current passing through them, but the current will depend on the potential difference. So I want to find a relationship between the properties of the light bulbs themselves. You see, you are on the right track. The power is given by V times I. But let me use this as V times V over R, so V squared over R. So if you have two light bulbs, their brightness will be proportional to the power that they use. So the ratio of their power will be V squared over R1 divided by V squared over R2. They are connected to the same potential. So the power ratio is just the inverse ratio of their resistances if you connect them to the same voltage. So what we need to do here is, what is the ratio of resistances of two light bulbs which have the same power at different voltages? You see, one of them has 75 watts, but this is labeled at V1, at a potential V1. And the other one is labeled as 75 watts at a different potential. Well, let's just take the ratio. So this just tells me that V2 squared over R2 should be equal to V1 squared over R1, or R2 over R1 is V2 squared over V1 squared. Now let's go back. P1 over P2 was equal to R2 over R1, which we now have seen that this is V2 squared over V1 squared. So this is not R, this is P. So P1 over P2 is actually, well, V2 is 120 volts divided by 220 volts. Well, this is something like 0.26. It will be almost 4 times dimmer in the States. So if you just take a light bulb from home, take it to the US, it will be just 4 times dimmer than what you would obtain if you had bought a similar, same labeled light bulb over there. Any questions on this one? Now let's try to connect resistors. Well, actually, we did connect some resistors, by the way, in the first problem we discussed. When we were looking at the cylinder with a cavity, we said that we can imagine it as very thin shells connected to each other. So that is nothing but you have different resistors connected what we call in series. Well, whenever you have any of these equipments, we already discussed the capacitors. We looked at capacitors in series. Now we have resistors in series. What you do is you let the current, the same current, passes through all of them. So you have the resistance R1, R2, R3, R4, etc. And they all carry the same current. It's the same current. Well, it was the same also in capacitors. But what we meant by connecting capacitors in series was basically the current we send through one of them just passes through all of them. Let's just start with just two of them. We send the current through it, the same current. So if we want to calculate the capacitance, the resistance of this circuit element, we have to determine the potential difference between these 2 points. Let's say A, B, and C. Potential difference between A and C is just the potential difference between A and B plus the potential difference between B and C. This we just call the potential difference V. Well, between A and B, what is the potential difference in terms of the current and the resistance R1? R1, I. Between B and C? R2 times I. So this is equal to R1 plus R2 times I. So the potential difference, as it should be, is proportional to the current running through my system. And the proportionality constant is defined as the resistance of my system. So if we have resistors connected in series, their resistances are just summed up. Well, in a sense, you can think of this as you are adding their lengths. You see, resistance was given by rho L over A. If you just attach one after the other one, you are increasing L. So you are increasing the resistance. You are just summing L, so you are summing the resistances. But this relation holds whether the resistors are of the same type, of the same material, or of different material, different shapes. This relation doesn't make any assumption on the shape. Whatever the expression is for each one of these, the sum of the resistances of resistors connected in series is always the sum. And then we have the other connection. Resistors in parallel. And in this one, the current is not the same current running through all of them, but the current is split, and different currents run through different ones. You send the current I. Let's say you first split it into two from both of them. So this is resistance R1, this is resistance R2. What is VAB? Let's say the current, you send the current I. Some of it will go through resistance R1. Some of it will go through resistance R2. So let's say I1 goes through R1 and I2 goes through R2. Now, what is VAB? The potential difference between those 2 points. I1 times R1. And at the same time, it's just I2 times R2. Because it doesn't matter how we go from point A to point B when we are calculating potential difference. We can go like this. Then the potential difference will be just I1 times R1. Or we can go like this. Then the potential difference will be just I2 times R2. So this already gives me what the ratio of I1 and I2 are. And I also know that I should be equal to I1 plus I2. Because you see, the total number of electrons moving along this wire should be nothing but the sum of the electrons coming from this wire and the sum of the electrons coming from this wire. The number of electrons that are moving do not change in the circuit. So the sum of these two should be equal to this one. Well, on one hand, I have I is equal to V over R. R being the total resistance of my circuit. On the other hand, I1, well, this is V. I1 is also V over R1. And I2 is V over R2. So this tells me that if they are connected in series, 1 over R is equal to 1 over R1 plus 1 over R2. If you make the analogy as summing the length, now if you connect them one parallel to the other one, you are summing the area. The area is 1 over R, so you should be summing the 1 over R's. Now, to avoid any confusion, let's just compare capacitors and resistors. In series, if you have 2 resistors, the total resistance is the sum. For capacitors, the inverse capacitance is the sum of the inverse capacitances of the other ones. And if you connect in parallel, well, their inverse resistance is the sum of the inverses of the resistances of each one of the resistor. And the capacitance, they are just summed. Any questions? Well, before I let you go, let me ask you a question. Let's say we have this circuit. We are sending a current. And let's imagine we are sending a current in that direction. And let's assume you are just an electron running through the circuit. As an electron, you just run through this wire happily, and then you reach this junction. How does this electron know whether to go left or right? How does it decide? How do the electrons that reach over here, they don't yet know what R1 and R2 are. They are just over here. How do they decide that some fraction should go up, some fraction should go down, such that this relation is satisfied? Okay, now you can go.